Basics of exponents. We start off where there's just a few rules where there's not really a way around it. You just kind of have to know them. And they all make logical sense, and I'm going to try to kind of demonstrate that here with this slide. So, if you start out with something like x cubed times x squared, that's like saying you have five x's being multiplied together. There's x times x for x cubed, and then x times x for x squared. So altogether, that's a total of five x's, x to the fifth. And we can look at those exponents and see that obviously those are going to add. Okay, now if you have x cubed squared, that's like saying x times x times x times x times x times x. So there would be then a total of six x's, so that would be x to the sixth. Okay, that's another property of exponents. We also have the situation where you might have x times y and then that whole thing is being squared. That is not xy squared, that is x squared y squared because we have two x's and two y's being multiplied together. So that ends up being x squared y squared. We also have situations where it's basically the same thing here. If we have x divided by y and they're both being squared, then we'd have x times x divided by y times y, which is x squared divided by y squared. And then finally, if we have like division here, if we have like x cubed divided by x squared, that's like having three x's, not 3x, but 3x, so x times x times x divided by x times x. There's just one x left over, right? If you cross out the two other x's. And so what you end up with is this, and we can generalize this and state the following rules. Okay, there's such thing as the product rule, where essentially if you're multiplying two exponents together, like if you now this notice something very important here is this a and this a are the same. If you have something like x squared times x cubed, that would end up being x to the fifth because you add the exponents there. Power rule, sometimes we call this powers of powers, we multiply powers. So if you were raising an exponent to another exponent, you just multiply the two exponents together. Because if you had, for example, in the last slide, we had x cubed squared, that was just ended up being six x's. So x times x times x times x times x. I don't know if I said it six times, but whatever. It'd be x to the sixth. So we have this rule here. It's the power rule. And then the quotient rule is when you have a to the m divided by a to the n. And we can actually do one more here. If we had an example like this and we had x squared divided by x cubed, this would be x to the 2 minus 3, which is x to the negative 1. And if you looked at this here, and instead you wrote it out as all the x's, x times x times x, cancel those two x's out, you'd see that that's 1 over x. And we said then that this is true and this is true, which means they're equal to each other. Okay, so which tells me another kind of rule here about negative exponents. So when you have a negative exponent, it's basically the same thing as having the reciprocal. And then this rule here bears repeating also. This is basically that the distributive property works for exponents too. If you have AB and that's raised to the nth power, then like A, B both are being raised to the nth power, then it'd be A to the nth, B to the nth. It is absolutely not A times B to the nth power. This is kind of a similar thing as when you have x plus y quantity squared and you say that it's x squared plus y squared. No, it's not that, okay? It's whatever's inside it. This whole thing inside the parentheses is being squared. So we'd multiply it by itself and we have to now distribute that out and stuff. So that's kind of the distributive property exponent works. Same deal here for when you have a fraction inside. And then, like we said before, negative exponents. So when you have this negative m, it's like saying, all right, I'm going to put the whole b, I'm going to put it on the bottom. It's a negative exponent. It's the same thing as a reciprocal. It also works too. If you had a negative exponent in the denominator, for example, if you had a to the n divided by b to the negative m, that is the same thing as a to the n times b to the m. I just brought that negative exponent and kind of put it up there. So it's all being multiplied now. Okay, so let's look at an example here. If we have a problem like this incorporates several of our different properties. Actually, it's just one of our different properties, but kind of a bunch of different times of the same property. First thing we can do is basically combine like terms. So we have here a number and a number, or integers and integers. We can multiply those together, so that would just be 45. Okay. We can also look at the x term. So we have x squared and x. So x squared times x to the first, that would just be x to the third. We have three total x's. And then finally, the y terms, we have y and y to the fourth, so a total of y to the fifth. And that's it. that is how you would multiply those together. You just kind of combine like terms. Here's an example of how the distributive property works for exponents. We'd have, this is not just negative 4 times x to the 12th, this is negative 4 to the 4th times x cubed to the 4th. So negative 4 to the 4th is positive 256. Okay, 4 times 4 is 16, times 4 is 64, times 4 is 256, and it's negative times a negative times a negative times a negative is a positive. Then this one is powers of powers, we multiply powers, so it would just be x to the 12th. Here's one that has a bunch of different things going on, a lot of negative exponents, and there's a couple of different ways you can do this, but you might as well start off by just doing the same thing we did in the first problem. So 5 times 6, that's 30. A to the negative 3 times a to the negative 6. So it would be a to the negative 3 plus negative 6, right? Because that's all we're doing is multiplying to the same variable to a different exponent. So we're just going to add the exponents. So that'd be times a to the negative ninth, okay? Then we have b to the negative 2, b to the 3. That's just going to be positive 1b, right? b to the first. And then c to the negative fourth and c squared, that's going to be c to the negative 2. And so all we have to do now is identify that there are two negative exponents here, the negative 9 and the negative 2. We're going to break those down to the denominator, and we're going to end up with 30b, right? The b still stays on top, divided by a to the ninth c squared. All the things we've talked about so far don't make any sense if this situation here is not the case. So b being the base, if b is greater than 0 and b is not equal to 1, and m and n are real numbers, m and n being exponents of the base, that means that n equals m. Okay, so in other words, another way to say that is if you have some base raised to some exponent, and then you have that same base raised to a different exponent, those two exponents have to equal each other. This is very, very, very important here. And it's kind of something that we can use to our advantage, especially when we get into the next unit, next topic, major topic of logarithms. This is very key. And so in this problem here, because 2 and 2 are equal, that means that x and 3 must be equal. 2 to the x is equal to 2 to the third. 2 to the third, x must be 3. Let's look at some examples where we have to, where it doesn't quite look like it works out where we're able to solve it, but we can by manipulating the base. Okay, here's a problem here where we can or actually both of these problems are ones where we can rewrite one of our bases to look like the other base. So we have to get a common base here. So it's usually easier to decrease the number. So it's easier to bring the 125 down to be a 5 than it is to make the 5 be a 125. They're both perfectly possible to do. But it's just going to be, I just recommend doing that. So we have 5 to the x, that's fine. Another way to write 125, right, is 5 cubed, 5 times 5 times 5. So in this case, that means x must be equal to 3. Now, here's the next problem here is a little more tricky. I have 5 and I have 1/25. So something you might see is that 1/25, right? Well, let's write 5 to the 2x first. Okay, 1/25 can be rewritten as 1 divided by 5 squared, right? That's the same thing. And then we have 1/5 here, but if I wanted this to be 5, I can make this a negative 2. So if I raise this entire thing to the negative first power, basically, I could say that 5 to the 2x is equal to 5 to the negative 2. Okay, and then I have same base, right? 5 and 5. So that means 2x is equal to negative 2, so x is equal to negative 1. Okay, so we can just manipulate each base to bring them to become common bases. This is a really important skill to have because sometimes we'll start talking about rational exponents where we have radicals and stuff, and we have to sort of instead of having radicals, we use rational exponents, and then oh, suddenly now we can convert bases and set exponents equal to each other. All right, we got 3 more examples. Here's 2 of them. This first problem looks like one we dealt with before. And so this 1/5 to the power of x plus 1, that doesn't look like something I want to mess with. In fact, this 1 over 125, that looks pretty easy because 125 is 5 cubed, right? So that's the same thing as 1 over 5 cubed, which is also, right, 1 over 5 cubed is also equal to 1/5 cubed, right? 1 cubed is 1, 5 cubed is 125. So what we can say then is that that is equal to 1/5 cubed. So that means that x plus 1 equals 3, so that x equals 2. All right, this next one here, now there's a few different ways to approach a problem like this because 16 and 64 have multiple common bases. 4 is the one I'm thinking of, right? Because we could say that 16 is 4 squared, that would still be to the x power, and 64, oh, let me rewrite that, 64 is 4 cubed. Okay, so you can see right away that that's going to work for you because that's just going to end up being 4 to the 2x, powers of powers, we multiply powers, equals 4 cubed, right, same base, 2x equals 3, so x is equal to 3/2. You could also have instead gone down to the lowest common base, and as you get farther into this, you'll find that that is actually a pretty good practice. But for now, we just show that example. So 16 is the same thing as 2 to the 4th, right? And that's to the x power. And then 64 is 2 to the 6th. 2 to the 6th. So now that would be 2 to the 4x power is equal to 2 to the 6th. So same base, that means the exponents are equal. 4x is equal to 6. X is equal to 6/4, which again is still 3/2. Now that seems like more work because you have to reduce it, but in the future you'll find that's actually a good thing. Okay, last problem here. The objective is we're going to want to get all of these to be the same base, and 2 of them already are, so let's make the 25 be a base of 5 also. So this would be 5 to the x plus 1 times, and then we can say that that's 5 squared to the x minus 3 equals 5. Now powers of powers, we multiply powers right here, so that'd be 5 to the x plus 1 times 5 to the 2x minus 6. We distribute the 2 into each of these. That equals 5. So now we have same bases, we're multiplying same bases together, we just add the exponents, so it'd be 5 to the x plus 1 plus 2x minus 6 equals 5, like to the first, right? And then that would be 5 to the 3x minus 5 equals 5 to the first. So that means 3x minus 5 equals 1, right? 3x minus 5 equals 1. 3x equals 6, so x equals 2. So that problem has several different things going on in it, but as long as we can get to a common base, all we need to do is do our exponent rules, set exponents equal to each other, and we can solve these equations.